uh, we continue our discussion on eigenvalue decomposition that we were doing in the last class. I just wanted to show something very interesting. Okay, so this article is from Siam News. Okay, so this article is from Siam News, recent article, October 1. So the title is Deep Learning, What Could Go Wrong? Okay. I'm just going to read this first paragraph, and you can relate it to something that we have been talking in the class, right? So if you remember, after doing this system of linear equations and everything, we had focused a lot on something which is called a sensitivity analysis, right? And what was this sensitivity analysis doing? The sensitivity analysis basically was telling us, if you perturb your input little bit, that means if you perturb A and B little bit, what happens to X, right? What happens to X? The X is the solution. So the output was X basically, and inputs were A and B. So if you slightly perturb these A and B, how much is the perturbation that you get into X, right? So that was the question that was being asked. And through condition numbers, through maximum and minimum magnifications, we were able to derive certain bounds. We were able to derive bounds on such perturbations, right? And I had told there are many places. So regression and all are straightforward examples where these type of things are really important. You want to know how much is the variation in parameter estimate and so on and so forth. But in deep learning also, this problem is very important. Okay, so I'll just read this and you can understand the importance of this sensitivity analysis. So in a field of research where algorithms can misinterpret stop sign as speed limit signs and so on and so forth. Okay, so the question that they want to ask is, are current artificial intelligence solutions are they sufficiently robust, resilient, and trustworthy? Okay, so how can the research community quantify and address such issues? That's the question that they're asking here. And many empirical approaches investigate the generation of adversarial attack. Okay, so what is adversarial attack? Small deliberate perturbations to an input. So try to relate it with Ax is equal to B problem, then you are trying to perturb B. Okay, so small deliberate perturbations to an input that can cause dramatic changes in system's output. Okay, so that is what adversarial attack is. And what are you doing? You are deliberately trying to put perturbations in the input that cause dramatic changes in systems output. So changes that are essentially imperceptible to human eye may alter predictions in the field of image classification, which has implications in many high stake and safety critical settings. Okay, so the rise of algorithms that construct attacks, that means that they will construct those small deliberate perturbations which will dramatic change in systems output. Okay, so constructing such attacks and heuristic techniques that identify or guard against them has led to a version of conflict escalation wherein attack and defense strategies become increasingly ingenious. Okay, so now here what is happening? A person who wants to attack, who wants to make an attack, they will deliberately perturb the input in a very small way. So you remember the example that we were taking, Ax is equal to B, that 100, 999, 999, 988, 998 matrix, and the output was addition of the columns basically. And then you gave a very small perturbation of the magnitude of 0.01 in a very specific direction, and that caused dramatic change in the system's output, right? So what was the output? The solution x1, x2, and that changed dramatically, right? So how to design such small perturbations, that means how to construct such adversarial attacks. And if you have such an attack, if you have such perturbations, then how to guard against them. Okay, so how to guard against them, what should you do so that your output will not be as perturbed as it is. Okay, so that is something that people are trying to investigate. Obviously all these things are happening in case of a neural network. Okay, so you think of neural network as something which is a huge function composition chain. Okay, so neural network is a non-linear function. You are sending in some input to the neural network, and neural network is giving you an output. So a small change, small perturbation in the input will may or may not lead a very drastic change in the output, right? So we have seen that in our own case, a very simple case of solving system of linear equations, right? So this is something that they're talking of, this adversarial attacks that they're speaking of, that is actually generalization of the sensitivity analysis that we were trying to do on the linear problem x is equal to a inverse b, right? So you were trying to find out solution. So then, they clearly say here, these issues concern the conditioning of the underlying problem and stability of the algorithms in use, right? So the conditioning of the underlying problem. So in our case, when you were solving ax is equal to b, the conditioning really meant you were talking of condition number of matrix, and that was giving you those upper and lower bounds and stability of the algorithm in use. Okay, so stability, I have been mentioning this backward stability of the algorithm a lot, but I have not actually formally done anything about that in this particular course. But that stability, like I discussed about, why do you want to use orthogonal matrices, because multiplication by an orthogonal matrix is backward stable algorithm, and so on and so forth. So these are the type of things I have been talking in the class but not formally doing. So these issues basically are concerning conditioning of the underlying problem. In our case, it is condition number, and stability of the algorithms in use. In our case, backward stability of the algorithms. Okay. And recent research has utilized mathematical tools, notably from numerical analysis, applied probability, and high dimensional geometry to shed light on this field. However, many open problems remain. Okay. So this is something that is really very interesting. And this is something that might be of interest to many of you who want to pursue research later on in your career, that there are many open problems that still are there, and you are asking to do sensitivity analysis, right? Basically, the question that you are asking here in this adversarial attacks is the question of whether you can do very nicely this sensitivity analysis. So obviously, the difficulty that will arise in doing sensitivity analysis in such cases is about conditioning of underlying problem. Because we had linear system, ax is equal to b, linear problem, the conditioning was relatively easy, right? Coming up with the concept of condition number and all, how this matrix A is affecting the input X and you are getting output B, how those circles are getting distorted into ellipses, and so to speak. That is what basically conditioning is, right? So here the function A was linear function, so things were really very easy to understand. But in general, the neural network that you will have, the function will be a huge chain of compositions of nonlinear functions. So resulting function will be nonlinear, it will be in a very high dimension output, the visualization will be difficult. So coming up with such sensitivity analysis results obviously is a difficult problem, and that's why you see heuristic techniques. Okay, so that's what people are doing, heuristic techniques, they're trying to investigate. So possibly a wholesome solution like condition number may not exist for these type of problems, but for a particular network, for a particular architecture, does there exist some theory, or can you look into that? So basically you are doing sensitivity analysis, right? So that's what I just wanted to say. So a very first step about sensitivity analysis that people are really trying to do in case of deep learning or deep networks is something that we already have done in our course, sensitivity analysis for system of linear equations. So apart from just mentioning about those sensitivity analysis results and saying that these are the parameters that we are estimating in regression problem, and those parameters we don't want them to vary too much, and so on and so forth, this is another interesting example where sensitivity analysis is really very important. Okay, so I just recently read this came in Siam News, this month's Siam News article. So this is very recent, like only 4 or 5 days ago this came, and I was just reading it, and I thought I'll just share it because some of you still may have little bit of skepticism about, this is too theoretical, why do you want to do this, and sensitivity analysis, where is it applied, and things like that. You may have these issues in your mind. So I just thought I will I'll share this article with you, and I'll just tell what is really happening. And then here, later on in this article, the authors very nicely take a linear separator. So they have two classes, and then there is a linear separator. So this linear separator is given by this W, and then this W transpose X is what they do, a linear separator. And based on whether it is greater than alpha or less than alpha, they decide whether the like two class classification problem they are trying to solve, right? So X is the data point. So find out this linear separator W, and W transpose X, you will just check with the alpha, right? If it lies if it is less than alpha, greater than alpha, based on that, you will decide whether it belongs to class 1 or class 2, right? And then what they are doing as an adversarial attack, they are like giving very small perturbations to this input X. So here input they are taking to be an image. So the vector X is basically, the column vector of all the pixel intensities, and then they are giving some perturbations to the pixel intensities, and then very nicely graphically they are explaining these things here, right? So this is something that they are talking about, and it is really very nicely explained. Like someone like me who has very minimal background in all these things also was able to understand very nicely what they were trying to say, and how what was the message of it. Okay, so there's a very nice article, very nice, nicely written, and I'll urge all of you to at least go through it once to make sure, like, you see how the sensitivity analysis is really very important. And this is something that people are trying to understand for functions which are non-linear. Basically, a simple baby step for us was we understood it in case of linear functions, and that conditioning was something that we did really very well in the class, I believe. And this conditioning, we were able to come up with some bounds on the output prediction, right? So that is something that we were able to do. I have not done stability of the algorithms in the class, but I have mentioned it in passing. Okay, so that is something that we typically do not do in this particular course. There is another course in maths department which I offer, which is computational linear algebra. In that course, I very extensively talk about the stability of algorithms and all the issues, like what is backward stability and all. And that is something that I do in that class, but not here. Okay, but this is a very well like developed theory for linear systems, of course, and people are trying to understand and possibly generalize it for non-linear systems. So I just thought that something that we have done already in the class, I'll just try to relate with very recent article and very recent news that I saw. So that's all I wanted to say about this. Okay, so that's all I wanted to say about this. I think if you have anything else to add to this, which will be beneficial for students in the class, yeah, please go on. Akshita, if you want to say something. So I have shared the link of this article in the chat. I hope you are able to see the link and open it. So in your free time, just read it, try to go through it, and see if you can appreciate and try to relate it with the things that we might have done in the course. Okay, so that's all I wanted to say. That's why I shared this. So I think now I can share the notebook, and we can start continue our discussion about eigenvalues. So anybody has anything to add to this, or if somebody has already worked in this field and have some experiences to share, please feel free to say that it will be beneficial for all of us. Please feel free if anybody has already worked in this field. Okay, then let us continue our discussion about eigenvalues, eigenvectors. Okay, so In the last class, what we were talking of were eigenvalues and eigenvectors, and we saw several cases, right? So the several cases that we saw were these, right? So I hope you remember these examples. And there were cases where eigenvalues were distinct. There were cases when eigenvectors were linearly independent. There were cases like this particular case where you did not get linearly independent eigenvectors, and so on and so forth, right? So there are a few things that we observed in last class. Today I just want to kind of generalize those things, and I just want to state few results related to that. That's what I want to do. So that's what I'll do today, and that will kind of set a base for us to understand singular value decomposition, and try to see what we can do, like prove the singular value decomposition possibly, and then take it from there, right? So that's what I want to do. So let us try to, like, as simply as I can. I'll just try to say these things. Okay. So there are several things that I want to say. So the first thing that I want to say is that let us start with a matrix A, which is a n by n matrix with real entries. Okay. So let lambda 1 and lambda 2 be two distinct eigenvalues of A with corresponding eigenvectors V1 and V2. Okay, so lambda 1, lambda 2 are distinct eigenvalues. So it is important that the eigenvalues are distinct. So if the eigenvalues are distinct, then what I'm saying, then what we have is that V1 and V2 are linearly independent. So that is the first thing that you need to observe. So if you have distinct eigenvalues, then you will always get linearly independent eigenvectors. Whatever eigenvectors that you choose, they will be linearly independent, right? So that is something that is really very interesting. Okay. So how do we prove this particular fact? So we have a v1 is equal to lambda 1 v1, and we have a v2 is equal to lambda 2 v2. Okay, that is what you have. We want to prove v1 and v2 are linearly independent. So if v1 or v2 are linearly independent, how do we prove that? You start with any linear combination of v1 v2. So consider this linear combination alpha 1 v1 plus alpha 2 v2, equate it to 0. So this is a linear combination which takes v1 v2 to 0. Then we want to prove that alpha 1 is equal to alpha 2 is equal to 0, right? So we want to prove that both these coefficients alpha and alpha 2 are 0. So the only linear combination that takes v1 v2 to 0 is the 0 0 linear combination, right? No other non-zero coefficients alpha and alpha 2 can possibly take you to 0. So that is what we have, right? So this is what we want. So you start with this linear combination. So you start with this linear combination alpha 1 v1 plus alpha 2 v2 is equal to 0. Because this vector is 0, alpha 1 v1 plus alpha 2 v2, when you apply a on this 0 vector, you will also get a 0 vector, right? Which is nothing but a into 0 is 0. Because a is a linear transformation, you will get this. I'll use the properties of linear transformation, and I'll also use the fact that v1 and v2 are eigenvectors. So what will I get? I'll get alpha 1 a v1 plus alpha 2 a v2, which is nothing but alpha 1 lambda 1 v1 plus alpha 2 lambda 2 v2 is equal to 0. That is what I get. Okay. So I see this as equation 1. I see this as equation 2. So there are two equations, 1 and 2 I have in alpha 1 and alpha 2. Right. So what I do, I multiply the first equation by lambda 1. Okay. Multiply first equation by lambda 1 and subtract it from 2. Subtract it from 2. Okay. So that's what I'll do. So multiply the first equation by lambda 1 and subtract this equation from the second equation. What will we get? So what do you get? Let us write down. So we get uh, so lambda 2 is getting multiplied. So alpha 2 into lambda 2 minus lambda 1 v2. Okay, so alpha 2 into lambda 2 minus lambda 1, alpha 2 into lambda 2 minus lambda 1, v2 is equal to 0. That is what we'll get. Now there are several things to note. So note that v2 is not equal to 0 because it's an eigenvector, correct? It's an eigenvector. Eigenvector by definition is not equal to 0. Further, lambda 1 is not equal to lambda 2. That is our assumption, right? We are considering two distinct eigenvalues. So distinct eigenvalues means lambda 1 is not equal to lambda 2, which means that lambda 2 minus lambda 1 is not equal to 0. So what does that mean? That means that the vector lambda 2 minus lambda 1 into v2 is not equal to 0. So this is not a 0 vector. So what does that mean? That means that the scalar alpha 2 has to be equal to 0. Only then you will get the 0 vector. So this is a non-zero vector. So this is a non-zero vector. And this non-zero vector is getting multiplied by a scalar and you get 0 vector, right? So if you are multiplying by a scalar to a non-zero vector and you are getting 0, the scalar has to be equal to 0. So that means that alpha 2 is equal to 0. And similarly, we can show that alpha 1 is also equal to 0. So what does that mean? That means that if you start with a linear combination, which is alpha 1 v1 plus alpha 2 v2 is equal to 0. If you start with this linear combination, then the only option for alpha 1 and alpha 2 is that they are 0. That means that v1 and v2 are linearly independent. That means that v1 and v2 are linearly independent. So this is something that is very, very important. What is very, very important? The thing that is really very important is that if you have distinct eigenvalues, lambda 1, lambda 2, then the eigenvectors are actually linearly independent. So you go back and see the examples that we were talking of in the last class. Anytime you saw two distinct eigenvalues, you see what were the eigenvectors. The eigenvectors were linearly independent. In R2, the eigenvectors were linearly independent, right? So you can check these things actually from these things, right? So one interesting fact that you can see here is the following. So what is it that you will observe here? So let me write it down. So suppose A is a matrix of the size n by n. Then we all know that there are n eigenvalues to this matrix. Let lambda 1, lambda 2 up to lambda n be eigenvalues of A, all distinct. Okay. These eigenvalues are all distinct. Then corresponding eigenvectors v1, v2 up to vn are linearly independent. Correct. So these are linearly independent, and because they are eigenvectors, what do we have? A vi is equal to lambda I vi for I is equal to 1 to up to n. Correct. So what is really happening? If v1, v2, vn are linearly independent for the lambda 1, lambda 2, lambda n, the eigenvalues, if all these eigenvectors are linearly independent, then what happens? Then the first thing to observe is that there are n linearly independent eigenvectors. So this set of n linearly independent eigenvectors in an n-dimensional space. So this will be a basis. Then this will be a basis of Rn. then this will be a basis of Rn. Okay. Then what will happen? So V1, V2, Vn will be a basis of Rn. So I form a matrix. I form a matrix T, which is nothing but columns of V1, V2, Vn. Okay. So I form a matrix T. So it is a matrix. So what is the size of this matrix? The size of this matrix is n by n. And I form this matrix T, which is nothing but columns of eigenvectors. The columns are nothing but eigenvectors. Then do you all agree that because of this particular relationship that I have, do you all agree that if I have AT, then this will be equal to T into lambda 1, lambda 2 up to lambda n? This is nothing but the eigenvector relation. This is from eigenvector relationship. Do you all agree that this is true? And because this V1, V2, Vn, they are basis of Rn. Because V1, V2, Vn are basis of Rn, this matrix T is invertible. Note that rank of T is actually equal to n, because columns of T are linearly independent, and because T is a n by n matrix, this implies that T is invertible, right? So if T is invertible, I can take inverse of T, and I can write this down as T into lambda 1, lambda 2 up to lambda n 0, 0 T inverse. And this process that we have done here is called as diagonalization of matrix A. This process is something which is called as diagonalization of matrix A. Okay, so A is equal to T lambda 1, lambda 2, lambda n T inverse, right? So this I will write down A is equal to T lambda T inverse. So this is diagonalization of A. Okay. Diagonalization of matrix. And why is it called diagonalization? Because by some transformation T lambda T inverse, you have been able to convert the matrix into a diagonal matrix, right? So if you want T inverse AT, T inverse AT will be equal to lambda, right? So T inverse AT and A, both of them will have same eigenvalues, that they are lambda, right? So this is something that is really very important. Okay. So is the diagonalization concept clear? So you start, so you have a matrix. Suppose the eigenvalues are distinct, then the distinct eigenvalues will give rise to linearly independent eigenvectors. If all the eigenvalues are distinct, then the eigenvectors corresponding to those eigenvalues will actually form the basis of Rn. And using that concept, you construct the matrix T of eigenvectors, where the columns of matrix T are nothing but the eigenvectors, and then you can write down A in terms of T lambda T inverse. Okay, so you can do this. So where T is this particular matrix of eigenvectors and lambda is actually the diagonal matrix. The diagonals of this matrix are nothing but the corresponding eigenvalues to the columns of T, right? So that's what you have done. So this is the diagonalization of a matrix A. Okay, so this is something that is very useful. This is something that is really very important. Okay, so this is one thing that you see. So another thing that you see is that A is a matrix in R n by n, and let lambda 1, lambda 2 up to lambda n be the eigenvalues, be the distinct eigenvalues of A. Okay. Be the distinct eigenvalues of A. So you start with distinct eigenvalues of A. Okay, so further let V1, V2 up to Vn be the corresponding eigenvectors. Okay, be the corresponding eigenvectors. So for any vector X in Rn, what can you do? You can write down X as a linear combination, unique linear combination of this alpha 1 V1 plus alpha 2 V2 plus alpha n V. Unique linear combination. So if you do AX, what will happen? What will happen? Alpha 1 AV1 is lambda 1 V1 plus alpha 2 lambda 2 V2 plus so on and so forth plus alpha n lambda n Vn. That's what will happen. Do you agree? Now if you do a square x, so again you apply a on this. So what will happen? You again take a of alpha 1 lambda 1 V1 plus alpha 2 lambda 2 V2 plus so on and so forth alpha n lambda n Vn. So what will this be equal to again? Alpha 1 will come out, lambda 1 and a V1. So a V1 is lambda 1 V1. So we'll get lambda 1 square V1 plus alpha 2 lambda 2 square V2 plus so on and so forth alpha n lambda n square Vn. That's what you get. Is that correct? Is that correct? Do you all agree? So in general, if I continue this process, continuing this process, what happens? At the nth iteration, what will you get? You tell me now. What will be a to the nx? What will be this a to the nx? Is that correct? And now what I do, I say that let lambda 1 without loss of generality lambda 1 without loss of generality be the eigenvalue with maximum magnitude. Correct? So what I really mean is lambda 1 is strictly greater than this lambda 2. Lambda 1 is strictly greater than lambda 3 and so on and so forth. So I can actually arrange the eigenvalues in descending order without loss of generality by their subscripts, right? Without loss of generality, I can say that this is the thing that is happening. And I am assuming that I am assuming the strict inequality here. Okay, so that is not without loss of generality. I am it may not be possible. It may be possible. We don't know. It may not be possible also. So the ordering is done, and this part is not without loss of generality. Okay, so let us say that let lambda 1 be such. Okay, lambda 1 be the eigenvalue. Let lambda 1, lambda 2 up to lambda n be such that I am able to arrange them in this particular way. Okay, let us not get into this without loss of. Suppose this is what is happening. Okay, and they are all greater than equal to 0, obviously. So because lambda 1 is strictly greater than lambda 2, lambda 1 is strictly greater than 0, absolute value. So it's a non-zero thing, lambda 1. So I can divide by lambda 1, right? So I will divide this equation by lambda 1 to the power n. Then what will I get? Anx divided by lambda 1 to the power n is basically equal to what? Alpha 1 v1 plus alpha 2 lambda 2 by lambda 1 to the power n v2 plus so on so forth, alpha n lambda n by lambda 1 to the power n Vn, right? So this equation that I have, this equation is basically same as this equation. I'm dividing both sides by lambda 1 to the power. This equation is same, right? No change, no problem. And now if I let this n to go to infinity, if I let this n to go to infinity, what will happen? What will happen?
Will tend to alpha 1 V1.
So it will tend to alpha 1 V1. So it will tend to alpha 1 V1, right? Because all these lambda 2 by lambda 1 to the power n, lambda n by lambda 1 to the power n, they all have absolute value less than 1, right? So if the absolute value is less than 1, any number c with absolute value less than 1, you take c to the power n, c to the power n will go to 0 as n tends to infinity. And what you see here is that as I take that n to go to infinity, I am left with this V1. I am left with this V1. And what is V1? V1 is the dominant eigenvector, so to speak, corresponding to the eigenvalue lambda 1. So a simple process that I am doing here, what is the process? I start with x, I multiply it by a, then I get ax, then I get a square x, I get a cube x, I get a raised 3x, a raised to 4x, a raised to 5x. Every time I do this operation, I keep on multiplying by the matrix A. And as this process tends to infinity, as this n tends to infinity, what I am left with is alpha 1 v1. So alpha 1 v1, alpha 1 is basically some scaling, right? So basically I can get alpha 1 v1. That means that I get v1 basically, right? So so this process actually yields the eigenvector, and once I have the eigenvector, then I obviously have the eigenvalue also. Lambda 1 I can compute from this. So so this idea that you see here, this idea that you see here, this idea actually leads to something which is called as power iteration or power method. To compute dominant eigenvalue. So dominant eigenvector first and then corresponding eigenvalue. Then corresponding eigenvalue. But what is important? The important thing to note here is that this particular condition needs to be satisfied, right? This strict inequality is important. If this strict inequality is not there, if the eigenvalues, like two eigenvalues are such that they have like same magnitude, then you don't know what will happen, right? You will get alpha 1 v1 plus alpha 2 v2 possibly, or you will get some a different linear combination of v1 and v2, and you will not be able to like take out anything between alpha 1 and alpha 2. Okay, that is something that is really very important. Do you understand this? Is that okay?
Sir,
Yeah.
even if lambda 1 is equal to one of the other lambda i's,
Yeah.
it only equal to one of lambda 2 to lambda n, right?
No,
It,
I'm saying that if you do not have this condition satisfied, mod of lambda 1 strictly greater than like one eigenvalue, if it is not strictly bigger than the remaining eigenvalues, one eigenvalue if it is not strictly bigger than the remaining eigenvalues, then you don't know what will happen, right? Because then this ratio, for example, this ratio also will be 1. If lambda 1 absolute value is equal to lambda 2 absolute value, then lambda 2 by lambda 1 absolute value, that ratio will be equal to 1. Then you will be left with alpha 1 v1 plus alpha 2 v2, some linear combination of v1 v2. You cannot say, so whatever vector remains at the nth iteration, that will be linear combination of v1 and v2. You cannot separate out v1 and v2 from each other. Do you understand that? Because I don't know what is alpha 1 and alpha 2, right? Because I don't know the eigenvectors to start with. So these alpha 1, alpha 2 are unknowns to me. Do you see the point, Aviraj?
yeah, but I just wanted to confirm that only two eigenvalues can have the same magnitude, right?
It is
Because of
not necessary. All eigenvalues also can have same magnitude. For example, identity matrix you take.
Okay.
The eigenvalues are 1, all the eigenvalues are 1, magnitude is same.
Right. Yes.
So we cannot say anything about eigenvalues, whether they have like only 2 are same or 3 are same. It depends on the characteristic equation, right? How the roots are. You can always start with same roots or roots with same magnitude. So for example, roots are on the unit circle. What are the matrices whose eigenvalues are on unit circle? You will see orthogonal matrices, right? So orthogonal matrices will never have this property. All the lambda i's will be equal to 0. You know, the roots are distinct. They all have same magnitude. Even if you have distinct roots, the magnitudes are same. So you will not have this property satisfied for the orthogonal matrices, right? So that's why this property is really very important. Is that okay?
Yeah, I got it.
Yeah. So that's what I really. So this idea that we have stated here, that actually leads to power iteration. Okay, so we will little bit later, like we'll have a very focused and possibly interesting discussion on this power method. But right now, this idea that I just said, that actually is helpful. Okay, so this is the concept behind power method. So when we speak of power method, when you see that, you will just realize immediately that what is really happening. So this is something that happens with distinct eigenvalues and correspondingly linearly independent eigenvectors. Okay, so this is what I wanted to say. One more thing I wanted to say is the following. So for example, um, so this is something that you would have seen. So I don't know how many of you have seen, but Markov chains with finite state space. So have you seen this Markov chains with finite state space? I hope some of you are at least aware of what are Markov chains. And so it's like you have finite number of states, and then you go from this to this with certain probability, this to this with certain probability. So this is what you'll do. You're going from one state to another. So you'll have 1 2 3 4. So going from 1 to 2, you can go from state 1 to state 2 with certain probability. You can go from state 1 to state 3 with certain probability, and so on, so forth, right? So these transition probabilities that you have, those transition probabilities, if you put in a matrix, right? So this is for state 1 to 3 different states, and then you will have from state 1 to state 1, you can remain in state 1 also. So that will also be with certain probability. Similarly, for state 2, you can have same thing. You can remain in state 2, or what is the probability of going from state 2 to state 1, state 2 to state 4, and state 2 to state 3, right? So you can have those probabilities. So all those probabilities could be written in a matrix. So you'll have a 4 by 4 matrix of transition probabilities. Okay, so you will have a 4 by 4 matrix of transition probabilities. Actually, there is extra. Okay, so you'll have a 4 by 4 matrix of transition probabilities, and let us call that matrix P. Okay, so P is such that all the entries of P are between 0 to 1, right? They are all non-negative entries, because these matrices. So this matrix P has this transition probability, right? So they are all probabilities, and you know that going from 1 to 1, probability of going from 1 to 1 plus probability of going from 1 to 2 plus probability of going from 1 to 3 plus probability of going from 1 to 4, they all are actually equal to 1. Summation will be equal to 1. So probability of going from 1 to 1, probability of going from 1 to 2, 1 to 3, and 1 to 4. Okay, so this will be equal to 1. So suppose you name this. So P21, P22, P23, and P24. P31, P32, P33, and P34. Okay, and then the last one is P41, P42, P43, and P44. right? So this is the matrix that you see. So you can see that if you take the sum, of all the columns, you'll get 1 1 1 1. If you take the sum of all the columns, you'll take 1 1 1. So 1 1 1 1 is actually equal to 1 times 1 1 1. Is that correct? This is saying that P11 plus P12 plus P13 plus P14 is equal to 1. So that means that this particular vector 1 1 1 1 is the eigenvector, correct? This one is the eigenvalue, and this is what you have, right? So typically what people look at for this particular matrix is a left eigenvector. Okay, so typically they look at left eigenvector, and that left eigenvector basically, so what people are interested in, so what we are interested in is the eigenvectors of P transpose. Okay, so typically what people are interested in is P transpose. So transpose of this matrix, so this transpose of the matrix people actually call is transition probability matrix. So one can easily see, so one can easily check that eigenvalues of P, eigenvalues of any matrix A and A transpose are same. Okay, this is for any arbitrary matrix A. Okay, so eigenvalues of P and P transpose are also same. Eigenvectors will change corresponding to those eigenvalues, but eigenvalues are same. Okay, this is not very difficult. Determinant of A minus lambda I, right? So you want to find out eigenvalues of A transpose. So you see the determinant of A transpose minus lambda, which is same as determinant of A transpose minus lambda I transpose, because I transpose is equal to I. Then I can use the property of transpose, and A minus lambda I whole transpose I can write down. But this is basically same as determinant of A minus lambda I, right? Why is that? Because determinant of A is same as determinant of A transpose. That is the property of determinant that you have seen. So basically the characteristic polynomial of A transpose is same as characteristic polynomial of A. So eigenvalues of A transpose and A are same for any matrix A. So P transpose and P will have same eigenvalues, but the eigenvectors will change. So what we are interested in, so we in particular are interested in the eigenvector corresponding to eigenvalue 1 of P transpose. Okay, so if this eigenvector corresponding to eigenvalue 1 of P transpose exists, okay, if it exists, then that has a special name. That name is called as stationary distribution of the Markov chain. Okay, so this is actually stationary distribution. And what is the stationary distribution? Stationary distribution, so basically this eigenvector V, which is the stationary distribution, will be 1, 2, 3, 4. Okay, four entries, and they will be the probabilities of being in state 1, state 2, state 3, and state 4, right? State 1, state 2, state 3, and state 4. So they will tell you the probabilities that you are in state 1, state 2, state 3, state 4. That's what this eigenvector is basically telling. And how do you do that? The way you do that is that you run the Markov chain for many time instances. So first time instance that you run, so you are in one of the 4 states, 1, 2, 3, 4, then you run the Markov chain, then you go to some other state, right? So initial state distribution, if you start and then you do P transpose, then you will get the state distribution of the next state. This is a simple probability calculation that you can do. Okay, initially you are in this state, then you are in this step. What is the calculation? You can see the calculation P transpose. If you multiply using the total probability law, you will get this probability. So this is only a you apply P transpose again on this, you apply P transpose again on this. Then after two rounds, after two runs of the Markov chain, what is the distribution? After three runs, what is the distribution? So you see what you are really doing. You see what you are really doing is something which is like this. You had a matrix, say you keep on multiplying. So you start with some initial vector x, and you keep on computing x, ax, a square x, a cube x. Here you are doing P transpose of x, P transpose of P transpose of x, P transpose square, P transpose cube, P transpose to the 4, and so on. So and if this sequence converges somewhere, where is it bound to converge? It is bound to converge to the stationary distribution. So the power method that we have, so this power method calculation that we have, it's directly related to the stationary distribution. Okay, so the calculation of stationary distribution. And in case of Markov chains, those who have exposure, they will realize that that exactly is what we are doing. In order to, we run the Markov chain for long enough time, and then you have the stationary distribution. If the stationary distribution of the Markov chain exists, then you will say that if you run the Markov chain long enough, what is the meaning of running Markov chain long enough? Doing this operation in the linear algebra, multiply this probability transition matrix to itself those many number of times. So you run the Markov chain for 500 times, you are basically looking at P transpose to the power 50. And what is the state distribution, probability distribution for the states at that 500 thing? That will be probably very close to the stationary distribution. That's what people really do. That's what really happens in Markov chain. Okay, so this is a very interesting application of this calculation, basically power method. So power method you can very nicely relate to this Markov chain theory. Okay, so that is something that I just wanted to tell. Okay, that's what I wanted. So I think the time is up. We'll stop here. We'll continue this discussion tomorrow, and then tomorrow we'll look at special type of matrices. First, we'll see symmetric matrices, and then we'll see orthogonal matrices. Okay. So symmetric and orthogonal matrices we'll see. We'll understand the properties of those matrices with respect to eigenvalues and eigenvectors, and then if there is time, we will look more closely about how one can compute eigenvalues and eigenvectors, though I'm not going to cover any numerical algorithm to compute eigenvalues and eigenvectors. I'll possibly focus only on this power method, this calculation, because this calculation is not very difficult. And if this power method iteration is clear, then possibly we'll try to understand this page ranking algorithm. Okay, so that's the agenda for the next week, but this is basically what we'll try to do. So is this okay? Any doubt about what we have done?
Sir, not a doubt, but can you upload last week's and last week's?
Last week's I forgot. I'll upload last week's. Yeah, I'll upload last week's. I'll check whatever is not there. Somebody I think wrote a message also. So September something. 17th September I'll upload whatever files are missing right away.
Also, sir, are we going to have any second test?
Sorry?
Are we going to have second class test?
Yes, we are going to have second